Check out these SpaceX engines. This is Raptor 1, Raptor 2, and Raptor 3. Which one do you think weighs the least? Raptor 3, of course. Now, which one do you think is more powerful? It's still Raptor 3. What about Blue Origin's most powerful engine, the BE4? Which one is more powerful, it or the Raptor 3? If you guess the BE4, you're wrong. It's still the Raptor 3. But which one weighs less? Clearly, the Raptor 3, by a large margin. And in fact, it's estimated to be nearly half the weight, meaning the Raptor 3's thrust-to-weight ratio is far superior, an essential metric for enabling high-frequency, cost-effective space travel. Honestly, the math is borderline insulting. While everyone else is spending tens of millions to build bulky, complex engines, SpaceX is cranking out these sleek, ultralight powerhouses that produce more thrust while being light enough to fit in the bed of a Ford F-150. It's the ultimate flex. An engine that is simultaneously the most powerful, the lightest, and the cheapest in its class, leaving the rest of the world fighting for second place. How the hell does SpaceX do that? Well, let's talk about it. This is the insane story of the radical redesign of the SpaceX Raptor engine.
The most common error of a smart engineer
piece of engineering so bold and complex.
The unprecedented step forward in rocket design
is to optimize a thing that should not exist.
It's July 25, 2019. SpaceX is preparing to launch Starhopper, their test rocket for Starship, on an experimental rocket engine many call the Holy Grail. Seconds later, Starhopper successfully lifts off into the air, and in doing so, ushers in a new age of rocket engines. The era of flyable, full-flow stage combustion cycle engines has arrived. In theory, it's relatively simple, but its implementation is insanely complex. First, both the fuel and oxidizer, originally around 10 bar, are pumped from their respective tanks into high-pressure turbopumps, where they are pressurized to over 300 bar. From there, the fuels enter pre-burners, where they are heated up to temperatures exceeding 600 to 800 Kelvin. In this gaseous state, they then power the same turbopumps they came from, after which they are fed into the main combustion chamber, where the hot, fuel-rich gas and hot, oxidizer-rich gas mix together and ignite. The chamber reaches temperatures in excess of 3,500 Kelvin or 3,000 to 6,000 degrees Fahrenheit, and the chamber's internal pressure exceeds 300 bar. The gases are then accelerated through the engine nozzles, where upon expansion they produce insanely high levels of thrust. Sounds crazy, but this is actually old technology. It was first conceived nearly 60 years ago with the Russian RD-270, an engine meant to propel the Soviets to the moon. However, following America's successful moon landing and subsequent conclusion of the space race, it was abandoned, as there is no longer a sufficient motivating driver for it. Today, though, SpaceX is ample of motivation, and even larger ambitions that demand such an engine. Colonizing the moon, postponed to Mars for now, requires no less. But in order to colonize the moon, and later Mars, SpaceX will need hundreds of operational starships. This necessitates hundreds of engines. Engines that will be reliable, reusable, and cheap. An engine that can be powered on methane, a clean-burning fuel that's also abundant on Mars. An engine that could be mass-produced at a rate no engine before had been produced. The Raptor 1 was an engineering marvel. In its current iteration, SpaceX would never achieve its goal. Raptor 1 was just too complex. But this was by design. Raptor 1 was a crucial development and testing engine. Belovingly nicknamed the Christmas tree, it was instrumented to death, covered from head to toe in external sensors, valves, and plumbing. The purpose being to collect as much data as possible to understand how this complex engine worked and operated under various conditions. Temperature sensors monitoring the pre-burners and combustion chambers, pressure sensors for the fuel and oxidizer lines, as well as the turbopumps, vibration sensors to monitor vibration levels in the system, and many, many more. Additionally, the instruments were not light. All that added complexity increased the weight of the engine and created a myriad of failure points. The real kicker, though, was the need for a heavy heat shield to protect the instruments from the hellish heat of re-entry. The heat shield itself needed its own support structure as well, and a fire suppression system was also needed. Altogether, the heat shield system and external components added over 60 tons of weight and complexity to the engines. As impressive as the engine was, in its current iteration, there was no way in hell SpaceX could ever use this to colonize Mars. It needed simplification, but they now had the data they needed to begin deleting.
The most common error of a smart engineer is to optimize a thing that should not exist.
Adding parts is easy, removing them is hard. But if SpaceX wanted to turn their dreams into reality, that was exactly what they would have to do. Christmas was over. It was time to take the tree down. Come on, that was funny. With a better understanding of how the Raptor 1 works, SpaceX was able to remove a whole host of sensors it no longer needed. Temperature, pressure, vibration, strength, etc. no longer needed. The torch igniter was also removed as they became redundant, because under the high pressure and temperature in the main combustion chamber, the fuels acted hypergolic. This means they spontaneously combusted, so there was no need for an igniter. Furthermore, through part consolidation, they simplified even more. Individual valves were combined into integrated valve plates, which helped reduce external plumbing, and many of those hinges mentioned earlier became permanent welds, helping to further reduce the weight of the engine. They also made an interesting choice. Usually a key parameter of an improved engine is a higher specific impulse. Think better car mile per gallon. In Raptor 2, they intentionally made it worse. They dropped the specific impulse by 1% by increasing the throat diameter so they could achieve more thrust from the engine, 230 versus 185. This improved the thrust-to-weight ratio, and essentially the rocket would ascend much faster out of the thick atmosphere and spend less time fighting gravity. It's a part-level compromisation for system-level optimization. Now, while drastically simpler than the Raptor 1, Raptor 2 still lacked the ability to be rapidly produced. Each Starship would need 39 Raptor engines, 33 for the booster and 6 for the spacecraft. To produce hundreds of Starships, they would need a much faster way of spitting out the engines, introducing additive manufacturing. Ambitious targets were set for Raptor 3. It had to be lighter, deliver 280 tons of thrust, and operate at 350 bar of chamber pressure. This chamber pressure is not only higher than the previous holder, the Russian RD-71, it also challenges the limits of what's even possible with current materials. To achieve this, the heat shield needed to go away entirely, meaning all necessary external parts had to be brought inside. There's only one technology that realistically allows for this: additive manufacturing. This technology allows engineers to create complex internal geometry that traditional manufacturing cannot achieve, integrating fluid paths directly into the structure. Elon Musk has even gone so far as to say that SpaceX has the most advanced 3D metal printing technology in the world. So the engine is still complex, but the complexity has been moved from the exterior into the interior. Design for manufacturing is now more key here. This results in a deceptively simple looking rocket. So simple in fact, that some didn't even believe it was real. ULA CEO Tory Bruno questioned publicly on Twitter whether SpaceX had shown a partially assembled engine. Gwen Shotwell, president and COO of SpaceX, almost gleefully shared a video of Raptor 3 running at full power, playfully making fun of Tory's statement and proving for all to see that their simple, sleek design was in fact fully operational. Engineering is a game of trade-offs, however. In rapidly consolidating everything internally, SpaceX drastically reduced the serviceability of the engines. If any internal component failed, the engineers would need to cut the engine open in order to repair it. The gamble was that through their relentless refinement and improvement of the engine, repair incidents would not occur as often, and should a part fail, it might be more cost-effective to just replace it with an engine sitting on the shelf, as they'll be producing so many. The results from Raptor 1 to Raptor 3 are truly astonishing. Raptor 1 had a thrust-to-weight ratio of 92:1, Raptor 3 190:1. That's an improvement of 106%. Raptor 1 had a chamber pressure of 250 bar, Raptor 3 350 bar. That's a 40% increase, and a world record. It's truly awe-inspiring to see the extent to which SpaceX has been able to ruthlessly simplify the Raptor engine. From the handmade Christmas tree R1 to the sleek, mass-produced F1-looking R3. It's truly a masterclass in engineering. Raptor 3 is now well into production, enabling the ultimate goal: high-speed reusability through a design so integrated and clean that it doesn't need external production. This is the engine and the manufacturing prowess SpaceX needed to shorten the gap between its ambition to colonize the moon and Mars and its ability to do so. With plans for Raptor 4 already well underway, that gap will only continue to shrink.